Let me share. The presentation is visible, right? Okay, so first of all, happy Independence Day to all of you. And so today it's the third week, and as you all know, I am a PMRF fellow from ISC, and we are doing this as a way to sort out some of your doubts and discuss certain concepts, and see if I can, help you with some problem solving. Okay. So in the last class, what we learned was to use this divergence, curl, and gradient, and know what they mean, and see how what is their physical significance, and how from there we reach to the concept of potential. We also learned about the Gauss's law mainly, and we saw how that is useful in helping us to solve for the electric field and also the potential for systems where there is a symmetry. Okay, so in this class we would so we'll go in a similar way. We'll discuss some of the concepts, and then we'll at the same time we'll solve some problems. And at last, if you have some doubts, we can try to clear them. Okay. And anywhere if you face any doubt, just let me know. Okay. So what we will discuss today is conductors and induced charges. Okay. So why is it important is you'll understand in the coming slides. So suppose you have a conductor, okay, and then you have put it in some field, right? And now if you are asked that what is the field inside the conductor, most of you might know the answer, some might not know the answer. So I'll anyways ask. So what do you think should the field be? Anyone? Anyone, any idea? If you have read it before, then it's fine. Otherwise, we'll discuss. But anyways, what do you think? So if you have some conductor and you have some field, so there is some charge distribution in that you have kept a metal sphere, suppose. So what would be the field inside the sphere? Anyone?
So, ma'am, is the charge uniform inside it?
So there is no charge on the conductor. It's kept in an electric field. So there could be charges around it. So suppose you have some charge distribution here and there, and then you keep a conductor. Okay. So now the conductor can be some metals. Like as an example, I took a metal sphere. Okay. So suppose and it doesn't need to be a sphere. It can be of any arbitrary shape, some conductor, and there's some field around it somewhere outside. Okay. So what would be the field inside the conductor? So somebody said
Then it will
zero.
be zero inside.
Right. So why do you think it should be zero? Why is it zero? See, even in the conductor, we know that there are free charges, right? The free charges are moving. So you'll have some. Yes, yes, go ahead.
The net flux that is in is equal to the flux that is out of the conductor. So the net effect would be zero on the conductor.
Okay. But okay, that's okay. But another thing is that, see, in all this consideration, what we have thought of is, so there'll be some flux coming in, some flux going out, and so the net flux is zero. So you can say that, so if you do E dot ds, then it turns out to be zero, right? But that's a mathematical way of understanding. But how physically, suppose you have a conductor, and you put it inside a electric field. So what would happen? There would be some free charges, right? And they are moving. So there are, suppose, some free electrons, obviously. So these electrons will obviously be affected by the applied field, isn't it?
Ma'am, the direction of the applied field will be opposite to that one. So the charges will get cancelled. So it will be resulting in 0.
So the direction of the induced field, there'll be an induced field, and that direction would be opposite to the applied field direction, right? So it is something like this, right? Suppose if you have some applied electric field, so the positive charges move in this direction, the negative charges move in the opposite direction. So there is a net field in the opposite direction. Now, when you have a conductor, what happens is these two fields cancel each other, okay? And so the net electric field inside becomes 0. We would later see that if it is a dielectric, that is not always the case, right? In a dielectric, we obviously will also have some kind of induced charges that would happen similar to this, but then it would not cancel out. There would be a net polarization that would happen inside this substance. But for conductors, what happens is it is equal and opposite, and it cancels the applied field, right? Also, another reason why this is so is because, so whatever charges that is inside the conductor is actually reaching the surface and is spreading on the surface. And from the energy point of view, if you calculate the energy, like energy of a conductor with charge on the surface, same charge on the surface and same charge inside, like inside in the bulk, you would see that energetically also, when the charges are on the surface, it's energetically more favorable. Okay, so it's more stable configuration. So that's why, so from all these arguments, you can say that the electric field inside the conductor is 0. Okay. And because the electric field is 0, if you use the Gauss's law, you would say that there is no net charge density inside the conductor. Okay. And whatever charge that is there, so if you now put some charge on this conductor, you would see that the charges distribute on the surface. So there is no charge inside, right? And a conductor is a equipotential surface. So why is it so? It also comes from this definition of potential. So if you see here, what will you see is that from any point A to point B on the conductor, if you take a line integral, that turns out to be 0, right? Because there is no potential difference between the two. So that's how it explains that if you move charges on the surface of the conductor, there is no effective work done. And that also leads to this explanation, which says that the electric field is perpendicular to the surface. Because if there is a tangential component, then charges will actually flow and respond to that field, right? And there would be some work done in that case. But what happens in conductors is that, as you can see in the image, the electric fields are always perpendicular to the surface normal, right? And so these are some of the characteristics of conductors, and it's very useful in understanding as well as solving different physical problems. Now, suppose if you have some charge Q here, okay, and because of the presence of the charge Q, there would be some induced charges, and we already know that the electric field inside the conductor would be 0. Now, what happens if you have something like this? So there is a conductor, and then there is a cavity, okay? And inside the cavity, you have some charge Q. So what would be the field here? Okay, and what would be the field inside the cavity? What do you think?
Ma'am, electric field is calculated by the formula KQ by R.
Electric field is calculated by the formula.
Am I audible, ma'am?
Yes.
Electric field is calculated by the formula KQ by R.
KQ by R. Okay, K is 1 by 4 pi epsilon 0. What do you mean by K here?
Yeah, the value of K is 9 to 10 to the power 9 Newton meters
Right,
per
right. 1 by
second.
4. Okay. 1 by 4 pi epsilon 0 Q by R square it should be, right? For a point charge. What you were saying is for potential.
Yes.
Right. But so that's the formula, that's fine. So what you mean is if you have some charge Q here, you would have some field here, right? That is what you mean? So I mean, you have a conductor, inside that there is a cavity, in the cavity there is a charge Q. Now, because of the presence of this charge Q, what would be the field here inside the cavity, and what will be the field in the bulk of your conductor? You know, like this is your conductor and there is a hole there. So what will be the field in the hole or in the cavity, and what is the field in the bulk of your metal or your conductor? So you have some charge and there can be some field because of this point charge, right? So by that logic, you feel that the field should be non-zero here. Am I correct?
As the medium is varying, the distribution of field would vary in the bubble as well as the outer shell.
Okay. But okay, so what do you think? What should be so both the fields here and here should be non-zero, and there should be some value depending on the distance and the variance. That's your answer?
Yes, it should be non-zero.
Okay. Any other answer? Okay, so if not, let us now look into the question in details. Okay, so it's right that you have some point charge. So there'll be some field lines emanating from here. So there'll be some. So even if you use the Gauss's law and if you consider a surface like this or some spherical Gaussian surface inside this cavity, it would enclose some charge, some net charge, right? So from that logic and also from the fact that so this is a charge and this would have some field lines. And because of that, you can say that there would be some net field in this region. Okay. But now what happens when you come into the metal or into the conductor? So because of this plus charge, what would happen? There is a net field generated, right? And because of the net field, you will have an equal and opposite minus Q charge on like induced on this inner surface. And again, because your metal is neutral, what would happen? So there'll be a charge distribution that would happen inside this metal surface or inside the conductor. So you will have an induced minus Q charge here in the inner surface, and then a plus Q induced on the outer surface. And because of that, there would be a net induced electric field, which would cancel the field that would be otherwise present in this region, right? Similar to this explanation, right? This explanation. It's so what it tells is there's some net applied field, and then the field inside gets cancelled because of this induced charges. So same thing would happen here. There would be a field because of this point charge, but inside the metal or inside the bulk of the conductor, inside this conductor, what would happen is, so it's a 3D structure. Imagine it to be a 3D structure. So inside this, there'll be a redistribution of charges. So there'll be induced charges on the on different surfaces, and the net field because of that, so the net induced field would cancel the applied field, which comes from this plus Q charge. Okay. So because of that, what would happen is there would be no field.
Can you repeat the previous point, please?
Yes, yes. Okay.
Can you
Yes,
please
yes.
kindly repeat it?
Okay. So what I mean is, so you have some charge, okay, some Q charge. So now there'll be field lines emanating from these charges. And now from this charge. So obviously there should be some field in this region, right? And it would go as 1 by r square as the distance from the charge increases, right? And even if you consider a Gaussian sphere inside this cavity, from Gauss's law also, you will see that there is a net enclosed charge, and you can see that there is a net field that you would get inside the cavity. So that is fine. But now what happens inside the bulk of the conductor? So this is a conductor, right? This thing. So imagine this to be a 3D object with a hole inside, and inside the hole there is this charge, right? So now when you come to the bulk of your conductor, using the same logic that we just explained, so using the same logic here, so here it says that you have an applied field, and the charges inside the conductor gets distributed in such a way that there is a net induced field which cancels the applied field, right? So same thing would happen here. What would happen is there would be, so because of this plus q charge, there will be an induced minus q charge on the inner surface of the conductor. And again, there will be a, because the conductor is neutral, so what would happen is you would again have some plus q charge induced on the outer surface, right? And because of all this redistribution of charges, you will have a net induced field inside the conductor, which would cancel the otherwise applied field that comes from this q charge, right? So by that logic, what I mean is obviously there will be some field here, but there would be no field here inside the bulk of the conductor. Is it clear to everyone? Okay, so this is what I mean, right? And even from the Gauss's law, now if you want to argue from the Gauss's law that why is the field 0 in the bulk, right? So that also comes like it matches if you take into account the induced charge that gets generated in the inner surface of your cavity here, right? You have a plus q charge and there is a induced minus q charge. So if you take a Gaussian sphere inside the bulk of your conductor, the net enclosed charge would be 0, right? And so even from that logic, you can say that the net field inside the conductor would be 0. Okay. So now let us try to solve this question. So you have an uncharged spherical conductor, which is centered at the origin. Okay, and it has a cavity of some weird shape, as you can see, and there is some charge q placed somewhere inside the cavity. So now you want to say that what is the field outside the sphere, somewhere here. So what would be the field? What do you think the answer should be? Anybody, any idea? Okay. So you have this plus q charge, right? Okay. Anybody has any idea? Who wants to share it?
It should be proportional to the charge.
Okay. And so how should the expression be?
Sorry, I don't know the formulas.
Okay. Okay, so let's see. So how it's a, so you'll see that you already know the formula. It's just maybe you cannot recall it at this moment. Okay. So suppose this is your charge, right? And why do you say that it should be proportional to the charge that is inside? So what is your argument for that?
Because in the sphere we have a cavity and charge is placed inside it. So I assume the cavity is through the sphere. So I understand that the charge is placed inside that unknown shape of cavity, and around that we have a sphere. So so definitely there should be some field lines. If you take the spherical surface outside, then there should be some field lines emanating out of that.
But we already know that the field inside the conductor would be 0, right?
Yeah, yes. I'm not saying anything about the inside conductor. I'm just saying, considering that outer shell, and out of the shell, we'll have some uh, electric field, and that.
So my question, if I have to frame it properly, is that so you have some charge here, and then you see that because of this rearrangement of charges, the field inside goes to zero, right? So how does this information, the information that there is some charge q here, so the field in this entire sphere is zero. Inside that somewhere there is a cavity and then there is a charge, right? But if the field is outside is non-zero and if it is proportional to q, then somehow the information is being transmitted from this interior of the cavity to outside, right? There's some communication. So how is that communication set? You understand my question? How
Ma'am, the
will
answer will be E is equal
okay
to Q by 4 pi epsilon naught R square. It's
okay
inversely
and
proportional. So,
to the distance, okay, and why do you think that should be the answer? So basically, like your answer is correct, but and even the first person who said that it's proportional to charge, that's also correct. But my question is that you have a whole sphere, okay, and inside that there is some hole, there's some charge q there. But how does that information that there's some charge lying inside that cavity is transmitted to some outside point, right? When somewhere in the middle you have a region of zero field. So how is this information being transmitted? Something like that, right?
That is because of the induction effect that is happening. This charge
Right.
will induce the negative, and the negative will induce the equivalent. I mean, if I'm keeping a charge of q, the equal amount of q will be distributed on the surface of sphere.
Right.
Uh,
Right.
so
Exactly.
because of that effect, it is getting distributed.
Right. So that's how, if you have some charge inside a cavity, that information reaches some point, or the effect of that charge reaches this point P. It's because of this induction, right? So Q minus Q and then plus Q on the surface of the sphere. It's correct. So because now, so what it boils down to is that now you have some plus Q charge on the surface of the sphere, and what is a field at some point outside the sphere. And then you can use your Gauss's law, and you would see that this is your answer. And it's independent of what the shape of the cavity is and what the placement of the charge is. Right? Clear, right? Clear to everyone? These are very fundamental things. Yeah,
yes,
right.
ma'am.
Thank you. Thank you. Okay. So now this is another question which is based on the same concept. So we are just trying to get hold of the concept properly. Okay. So now you have these two spherical cavities inside this sphere of different radius. So you have these two cavities of radius A and B, and there's the overall big sphere has radius R. And now you say that at the center of each cavity, there is a point charge, okay, QA and QB. So what would be the surface charges on this surface, okay, the inner surface of the cavity, this cavity, and then this cavity, and what would be the surface charge on on the surface of this bigger sphere? What would be the answer? What do you think?
The main sphere, the bigger sphere, will have not the A and B point. The, the bigger sphere will have the charge equivalent to some of these two charges, Q and QB.
Okay. So what would be sigma R? Sigma is the surface charge, right? So how do you define surface charge density? It's defined as the total charge by the surface area, right?
Yes, then for the complete sphere, it should be the total charge enclosed by that sphere
Hmm.
divided by the total surface area of that bigger sphere. And I do not
Right.
know about the internal spheres.
Okay, so let's try to answer. So you're correct. So the total charge is QA plus QB, right? And what is the surface area of the bigger sphere? it should be 4 pi r square, right? So by that logic, sigma r should be QA plus QB by 4 pi r square. Okay, clear? Now we want to say that what would be the surface charge on this surface. And my hint is that you have to use the Gauss's law. Try to use the Gauss's law. So if you
For QA, it should be QA, and QB, it should be QB.
like
Opposite,
those are the
opposite
enclosed
effect. Minus
opposite.
QA and minus QB.
Why minus? Why minus? See, you want to find the surface charge. Oh, okay. I understand. You are talking about the induced charges. That's why, right?
Yes.
Okay. That's true. So you have some, if it should be minus QA by 4 pi r square, this should be minus QB by 4 pi r square. Yeah, correct. Because it would be induced charge. Correct.
Again, here comes the case. I am not considering the, like, I'm treating individually. If what would happen in the superposition effect, we need to, that is to be derived. Like if it is a separate case, a separate bubble, then minus QA would be okay for that thing. But what would be the effect of minus QA, the induced charge, because of the
On
next
this.
bubble? That
No,
I
that's
do
the
not know.
case. So these are
Yes.
there would be no effect because see there is no what do I mean? There's no communication between these two, right? You understanding, right? This is so how do I? So I mean, how is this two effects coming to the surface is because of the induction, but there would be no induction because of this charge on this surface. You understand, right? Because there's
Okay.
no communication between these two. These are all secluded cavities. So because that's the reason that in the entire QA charge, the negative of that gets distributed on this surface. Okay, and the entire minus of this charge gets distributed on this surface. You understand, right? So
Okay.
effectively, you cannot have extra induced charges, right? It should add up to the same value. So it should be something like this, right? And why are we putting r equal to a, b, and r? That is known to all of us, right? Because we are finding the surface charge on the inner sphere, like on this sphere. So we will put that radius value. Okay, so it should be r equal to a here, r equal to b here, and r equal to capital R here, right? So now, given this condition, what should be the field outside the conductor? So it's similar to what we just solved in the last question. So if you have some point P here outside, what would be the field there? Just use the same concept that we used that discussed in the last slide.
We can treat that as a net point charge itself, right? The point charge value is QA plus QB, and at point P, external point, from the distance between the center of sphere to that point, we can find it and calculate
So
the
it should
electric
be
field.
some 4 pi r square, 1 by 4 pi epsilon 0, QA plus QB by r square, where r is the distance
Yes.
from the center, right?
Yes.
And you can also do it using the Gauss's law, right? So you can consider a Gaussian surface with some radius small r, okay? Something, like consider, suppose if you have some point P here. So considering that P on some surface of a sphere of radius equal to that radial distance, okay? So you can consider that Gaussian surface. And so the net charge enclosed would then be QA plus QB, right? And so you can find the net electric field, right? So Gauss's law always holds. Okay, so whenever you are trying to understand how this induction is happening or how you have some charge, so what would be the induced charge on the inner surface, outer surface, always try to relate it with your Gauss's law explanation, okay? And see if it is making sense. Right. Now the thing is, what is the field within each cavity? So what would be the field? So what would be the field somewhere here, maybe? So this will also explain that why this charge has no effect on this sphere or the charge distribution here. This will also explain, this question will also explain that. So you want to find electric field at some point inside this cavity. And how should we proceed with that?
In that
Ma'am,
case,
it will be.
Yeah,
I'm
yeah.
sorry.
One by one. Go ahead. Go ahead. Yes.
For the field within each cavity, for the A part, it will be 1 by 4 pi epsilon naught Q by R A square. And for B, it will be 1 by 4 pi epsilon naught, then Q by B square.
Q by B square.
Radius of-
Okay.
Radius of B, I'm sorry, radius of B.
Yeah, but so that's the point. That so was there any other answer? I think somebody else also wanted to say something.
uh, I also had the same point. That is charge divided by the distance of that point to the charge of any sphere, the QA or QB.
Right. So what I just want to clarify is that, so you want to find, suppose, the charge at some point here, right? So then you have to consider a sphere with this radial distance. Okay. So the field will, you understand, right? It should not be 1 by 4 pi epsilon 0 QA by A square. It's A square only on the surface, because then that's the radial distance. Somewhere inside, it should be the radial distance from that point. Clear, right? So it should be something like
Yes.
this, right? Okay. So now if you look at this answer, one second. Okay, so if you look at this answer, you'll understand that, see, the field anywhere inside, okay, has no effect of this charge. Again, this charge has no effect on this, okay? And in the same way, like, there's no communication or no effect of this charge on how charges would get distributed inside this cavity or this bubble, right? So that explains why you don't have to consider that things here.
Understand. I will say the no effect thing.
Yes, yes.
Can you please repeat the last point kindly?
Yes, yes. So what I meant is that, see, so anywhere inside the cavity till you reach the surface, right? So you can see that for this sphere or this cavity, there is no effect of the charge that is there in this cavity, right? When you're calculating this, there's no effect of QB here when you calculate any field in this cavity till you reach the surface. So that also explains that the charge that is getting distributed on the inner surface of this cavity has nothing to do with what is here. So I wanted to just like clarify that part. So whatever charge QA you have, the equal and opposite charge gets distributed on the surface of this cavity, and same goes here. But there's no communication between these two. And even inside, if you find the field for any point inside each of these cavities, those are independent, because, see, this is not enclosed, right? So if you consider a Gaussian surface, this charge is not enclosed there, so it has no effect there. So the flux lines would actually cross. It would enter the sphere and cross the sphere, right? So there will be no net influx or like no net effect of electric flux. And that's why there's no effect of this charge on this or this charge on this. Is that clear?
Yes, ma'am.
Right. Now, what is the force on QA and QB? What do you think the answer should be?
That will be 0.
Right. That also explains the same thing, right? These are all isolated points. So if it was in free space, obviously this charge would exert some force on this, right? And vice versa. But that's not happening here. Understood, right? So the net force on QA and QB should be 0. Fine. Now what happens is you bring another third charge QC somewhere outside, okay, and near the conductor. So how would these values change in that case? What do you think?
The
So how
electric
would
field,
yeah. Yes, tell
the
me.
electric field will get modified, will get changed.
Okay, so all the 3 electric fields or which electric fields?
No, the other quantities will not change. The one which is outside the electric field, if you want to find out outside the conductor, that will change.
Okay, so E out will change,
Yes, that
right?
will. Yes, because
Okay, and
according
what about sigma A, sigma B, and sigma R?
to those will not change.
Okay, okay, so let's see. So as you can see here, sigma R changes. Why? Because when you bring this charge,
I
you
meant to say
bring,
that my AD will not change
hmm?
because you already gave an explanation while you were answering the answer number 3, right? So according to that, the sigma A and B will not change, but the R will definitely change if you bring a third one. So yeah.
Right, right. So whatever happens on this surface, that gets changed, right? But the values that are inside, sigma A, sigma B, or electric field inside these cavities, they don't change because of any charge that is outside the conductor, right? So physically, if you now think, this refers to some kind of a shielding effect, right? So whatever charge, whatever field, whatever is outside has no effect on these cavities. Okay, no effect on the field that is inside these cavities, no effect on how the charge is distributed inside these cavities. If you have some charge here, obviously that will affect the field outside, but not the other way around, right? So it's kind of a shielding effect that we can see, some kind of a caging effect, right? Okay, so I guess it's clear. So now let's move on to the next section, okay? So here, note, we have a metal sphere of some radius r, right? And it's carrying some charge q. So this metal sphere carries a charge q. And then it's surrounded by a thick concentric metal shell with inner radius A and outer radius B. Okay. So now the shell carries no net charge. So there is no net charge on this shell. There is only charge on the metal sphere plus Q. So now find the surface charge density sigma at capital R, at A and at B. What do you think the answer should be? So what should be the surface charge density at capital R?
It should be Q divided by 4 pi capital R square.
Epsilon naught capital R
Yeah,
square.
yes, the constant plus constant.
Ca-
Yes,
Oh, no, no, not epsilon naught, because it's surface charge density, right? It's not the field. So it should be surface, like the total charge by the surface area. So it should be
yes.
just, yes, right. So it should be Q by 4 pi capital R square, right? And what should be the charge on this inner surface of the shell?
Inner surface is same thing. Instead of R, the if the radius is A means then we need to divide by A or B. A then divided by Q divided by 4 pi A square. But we can put a negative sign on it because of the induction effect.
Right. Okay, right. And for B, it should be again same, but it would be plus Q and R will be equal to B, right?
Yes.
Right. Okay. Now, what should be the potential at the center? So, what should be the potential at the center of this sphere?
0.
Okay. Why do you say so?
It will be zero because potential is basically the work done for bringing a charge from infinity to that point, right? So yeah.
Okay. So, okay. So let's see. So this is correct. But now let's see here. So the explanation is correct. The work done for bringing the charge from infinity to the center of the sphere, right? And that mathematically is equal to E dot dl, right? Line integral of this from infinity to the center minus of that. That's just convention. Okay. So now if you do that, so you have to in for that see what is the field inside the metal conductor, what is the field in this region, and what is the field inside the in okay, and what is the field anywhere outside from outside to the shell. There are the three regions, right? This region, this inside region, and the inside of the metal conductor, right? So inside the metal conductor we know that the field is 0. So this is 0. Now what should be the field here? Somewhere between, like in this white region between the shell and the sphere, what should be the field? There should be a net field, right? Why? Because you have a net enclosed charge there. You have small q charge on this sphere, and there is a net charge. So if you consider some okay, so if you consider some pardon my drawing, okay, so it would be very bad. Anyways, so this is a sphere. It doesn't look like, but so if this is a sphere, okay, of some radius r, where r ranges from capital R to A. So somewhere in this region, what would be the field at some point on this sphere? It should be a non-zero value, right? Because it encloses a net charge of small q. And what should be the field somewhere here? So if you take some point here and, like take again, take a, I'm not drawing it, but some sphere here, and then there's a net. So if you want to find the field here somewhere outside, there'll also be a net field, right? And that would be equal to, so if you have plus q here, you would have minus q on this inner surface, and again plus q here, right? So the effective field that we'll have at some point outside would be equal to q by 4 pi r square. So that's what you see here, right? So from anywhere, any points from minus infinity till b, till the outer shell surface, this is your electric field. I can't see my pointer. So this is your electric field, right? Now inside this small thickness, obviously field is 0 because it's a metal shell, right? So inside metal bulk, inside conductor, it's 0. So in this region, it's 0. But again, between A to R, it's non-zero because it has a net enclosed charge, right? And that would be equal to, again, 1 by 4 pi epsilon 0 q by r square, where r ranges from A to capital R, right? And then again, inside, it would be 0. So if you do that, you'd see that you have a net potential at the center of your metal sphere. Is this clear to you? Clear to all of you? Right. So this in a way also tells you that if you have, so if you want to find potential at some point, you can use Gauss's law and whatever means to find the electric field and then use this integral definition, right? So this is important because the other way around, so if you want to find the potential, obviously, then you have to use another identity, which is the relation which relates electric field to potential. And that is given as E equal to minus grad V, right? So there, if you have, so here you have the electric field, you're finding the potential. The other way around, if you have the potential and you want to find the electric field, then you have to find the gradient of your potential, right? So this thing is important because I think even in your assignments, you have some questions where there's some charge distribution that is given. So rho is given, and then you are set to find the electric field maybe. So there also you're using a similar relation. It's like divergence of E equal to rho by epsilon naught, right? So your rho is given. Now you want to find E. So what do? So you obviously integrate, right? In order to find E. So where like this kind of differentiation and integration relations between coordinates would be very helpful in finding physical quantities. Okay, so try to remember that. So this is how you go from electric field to potential. Okay, so now the outer surface is touched to a grounding wire, okay, which lowers its potential to 0. So what happens is, so the potential of the outer surface goes to 0. Okay, so how will the answers in A and B change? Any idea?
Surface charge of the inner sphere remains same, whereas the surface charge density, whereas the outer thing will
So
drop to
this
0.
thing will drop to 0,
Um,
right?
yes, sigma A, sigma B will.
Sigma
Okay,
B is for the outer surface, like here,
okay,
the
sigma B
surface of
will
the
drop to
shell.
0. Sigma A, I don't know. Sigma R will be the same.
Okay, okay. And what would happen to your potential? So in this potential, you have 3 contributions, right? This is the contribution of the inner, like the metal sphere. This is for coming from the outer surface of the shell. This is coming from the inner surface of the shell, right? So now what happens, what is said here is that the outer surface potential goes to 0. So how do you think the potential should change? Potential at the center.
Uh, the first term, infinity to B, that terminology will become 0 because already I'm maintaining the shell outer thing as a 0 potential. So
Right.
the balance thing has to be calculated.
Okay. So that means what would happen? You don't have to calculate anything. So only this term would go away, right? Because this is 0. This potential is 0. So only this thing remains, right? You have already calculated it, right? So it should be something
Yes.
like this, right? Okay. Okay. Right. So this was to get used to this, the concept of induced charges, the concept of finding potentials on different surfaces, and how the induced charge can affect your electric field and the potentials, right? So now we'll move to another section, which is about capacitance. Okay, and here, so basically, if you have to naively define capacitance, is that so voltage, as you can see, is proportional to charge, right? And that proportionality constant is termed as capacitance. So how much charge corresponds to how much voltage? So that relation, that proportionality constant is given by the capacitance of your system, right? So now before doing that, I would just brush up about this thing, that suppose if you have some surface, okay, this is important. So important to remember how we reach to this definitions. So that's why I just put it here. So as you can see that if you have some charge and there's some sigma, surface charge density. So there, if you take a pillbox kind of thing like this, some Gaussian pillbox, and then there, if you want to use the Gauss's law, okay, so what you see is that there is a discontinuity between the normal component of electric field above and below this charge sheet, right? And that is given as sigma by epsilon naught, while the tangential component is continuous, right? Because so that comes from the Gauss's law, as you can see. So here, if you so if you do this integral, you would see that E dot dl goes to 0, and that so this comes from Gauss's law, and this is from the continuity, the line integral concept. So what happens is epsilon is very small, okay, and because of that, when you do an integral, it would be E into L minus E into L, because as you can see, the directions are opposite, right here. So you are doing a complete closed integral over the surface. So from there, you get to this point that the tangential components of electric fields are continuous. Okay. And So effectively, if you have some surface charge over some surface given as sigma, some charge density, then the electric field would be given as sigma by epsilon naught n cap, where n cap is your normal vector. Okay. And now you can write sigma is equal to epsilon naught into E, right? Electric field. And then you can use the definition of, so what is this? This is the same relation which is E equal to minus grad, right? That's what you have used here. So this in a way says how, if you are given the surface charge density, how can you find the potential? Okay. Or if you are given the potential, how do you go to the surface charge density? And this is useful in solving for like the concept of potential is very much into solving capacitance. And obviously like because you have this dependence, right? So you need to know the potential, and then you can go to, you need to know the charge on the surface, and then from there, or on the on the system, and then you can find the capacitance. And in order to find the potential, sometimes these relations are very useful. Okay. So this is something I think most of you know. So I would go a little fast in this. So it says that if you have two plates, right? And so it's like a parallel plate capacitor. But this thing is a very standard example of solving like a very standard question. So here what happens is you have this two infinite parallel plates. Okay. Here you have plus sigma charge density. Here you have minus sigma charge density. And now if you look at how the fields are, you would see that outside they would cancel. So there's a net field inside or between these two plates. Okay. And that is given as sigma by epsilon naught, right? So now if we know that information, and if you want to find the capacitance of a parallel plate capacitor, so now you consider same thing. Okay. So now you have two surfaces and the distance between them is d, and you want to find the capacitance. Okay. So how? By using this definition of capacitance and using the relation that you know that the field inside or between this two plates is given as sigma by epsilon naught. How do you find the expression for the capacitance? Can anyone let me know? What do you think? You might be already knowing the expression, but how do you get to that?
The expression is E epsilon naught A by D.
Epsilon naught A by D. What is E?
Epsilon naught A by D, which is
Hello? Hello? Okay, but how do you get to that? So you know that this is your field, right? This is your field between these two plates. So the two informations known to you is
8.85 into 10 to the power 16.
okay. There was some thing I just lost you. What did you say? Can you repeat?
Ma'am, I think because I think I am only wrong because you are saying, so I think I am wrong now.
No, I can't understand what you are saying. I just I could not hear properly, so I don't know whether you are right or wrong. So what I meant was that so epsilon naught A by D is fine, but I mean that how do you get to that expression if you start with just two information? One is that you know that the field between these two plates is sigma by epsilon naught. Okay. And another thing is that C is given as Q by V. So what is the first quantity that you have to find from there? The first quantity that you have to find is the potential, right? So now if you know that this is your field in this region, so how do you find the potential? Right? So there you have to use the relation of the relation between electric field and potential. So electric field is given as E equal to minus grad V, right? And V is given as minus E dot dl. So in a way, if you know that all throughout this region, your electric field is given as sigma by epsilon naught, then the potential in from going from one surface to another, so what the potential difference between the two would be given as sigma by epsilon naught into d, right? E dot dl. So you multiply the length or the distance with the electric field. And here electric field is not a function of distance. It's a constant value given as sigma by epsilon naught, right? So if you integrate, sigma by epsilon naught would come out and the total integration will be over d. So the potential difference between these 2 points, these 2 plates would come out to be epsilon naught, sigma by epsilon naught into d. So now you know V and you know that Q is the total charge and that would be given as sigma into A, right? Sigma is the charge per unit area. So sigma into A is equal to capital Q. So if you use both of these relations, you can find the expression for C. So that's how you get to this expression, right? So this is your expression for V and this is your expression for C, right? See, here you have used this relation. So I mean, this is how you reach to this expression using this two information, that what do you mean by capacitance and what is the field between these two plates. So this same concept, why I'm stressing on this fact is because in all the other kinds of capacitors that we will just discuss in the coming slides, you would see that we would use the same concept. So we would see what is the field. We would try to find the potential difference between these two surfaces. Basically, we want to find the potential difference between these two plates, or if it is concentric spheres, we want to find the potential difference between concentric spheres, and then use how we want to see how the charge density is related to the total charge. Use this relation to find the capacitance, right? So that's why I wanted to stress on how we reach to this expression. Okay, and as you can see, it is dependent on A, that is the area. It is dependent on D, but it's not dependent on Q, right? So how much charge is there on the surface is actually not making any difference to the capacitance. Okay. So now, if you have two concentric spherical metal shells, so these are 3D shells, okay, spherical shells, and then you have plus Q charge here and minus Q charge here. So how will you find the capacitance? So what should be the first step that we should do? Anybody, depending on what we just discussed? Okay. So depending on what we just discussed, the first thing that we have to find is we have to find the potential difference between the surface of this shell and the surface of the bigger shell, right? So if you do that, we have plus Q on the inner surface, minus Q on the outer surface. So the field between the two spheres would be given as 1 by 4 pi epsilon 0 capital Q by R square, right? Because that's the charge that is enclosed. So if you have some Gaussian surface in this region between the two shells, this should be the net enclosed charge would be capital Q, and this is the field, right? So and then now if you use this information, we can find the potential difference, right? And the potential difference between, we want to find the potential difference between this surface and the outer shell surface. So the integration runs from B to A, right? So this is your potential difference. Now, once you have found the potential difference, things are very easy. You know the definition of capacitance, that is given as Q by V, right? So you just have to divide by, use this formula. So put V, expression for V here, and then you reach to the expression for capacitance, right? Okay. Now, another thing that is important in understanding, or in when we talk about capacitor, is that, so basically when we charge up the capacitor, what we are trying to do is we want to increase. So when will the capacitance increase, right? So if you want capacitor charge increase, that means you want to increase Q. Okay, so that means you want to take electrons from this negative surface to the positive surface, and that would result in some work that has to be done, right? So if you say that the potential difference is given as Q by C, because C is given as Q by V, right? So from there, you know this is your potential difference. Anybody, any doubt? Okay. So if you know the potential difference, then you know that what is potential difference. Basically, so it's for unit charge. Now, if you want to move dq amount of charge, then you have to multiply by dq, and that would give you the work done, right? So that's how, if you use this expression, so q by c is for unit charge, that is the potential difference, and you multiply by dq. So that is the amount of work that has to be done in order to take dq amount of charge from the negative plate to the positive plate, right? And then if you want to charge up your capacitor to some charge capital Q, you do an integration from 0 to capital Q, and this is your W. So this is important because this is the work that has to be done to charge up the capacitor, and this is somehow linked to the energy, right? This is the energy store. So this is another important concept. That's why I discussed. Okay, so now the same concept that we did for the spherical shells, we want to do it for this coaxial metal cylindrical tubes, right? And again here, what should be the first step that we should do? Now you should be able to answer that. So if you are given to find capacitance of any structure, okay, so what should be the first thing that you should try to do?
Potential on the surface of A and potential on the surface of B.
And find the
we
difference.
can find the difference of potential between these two, and from that capacitance can be found out,
right?
From the Q value.
Right. So what we will do here is similar thing. So in order to find the potential, we need to find what should be the field between the two, right? So if you know the field, you can do an integral E dot dl
Sir,
from A to B.
my answer is coming. The capacitance is Q by 4 pi epsilon naught ln A by B.
Okay. Okay. We haven't solved for it yet, right? So let's try to solve it. We might reach the same answer. Right? We haven't solved it yet. We just started solving it. So basically, see, you want to find the potential. So that's fine. So if you want to find the potential, what? Okay. So ln, so the ln b by a, or that you got it for this question, right? Or did you get it for some other question?
No, for the cylinder only.
Right, right. So that we will solve now. So we'll see how we get to that. So that you don't have to remember this. This comes from this basic idea of finding potentials and using the definition of capacitance. Okay. So, and in order to find potential, what you have to find? You have to find what is the field in this region between these two surfaces. So for that, you use the Gauss's law, right? You consider some Gaussian cylinder of some radius small s. So the what do I say? The curved surface area would be given as E into 2 pi s into L. And then if if lambda is your what do I say? If lambda is the surface charge density, or the length, along the length, if that is the density, then it should be lambda into capital L. That should be your enclosed charge in the Gaussian cylinder. So we have taken that as Q here. Okay, so Q enclosed is given as Q here. And then from there, you find the electric field between these two surfaces. And then you use the same relation, that is the integral, right? And when you do that, this is the expression for the potential difference that you get. And now you use the definition of capacitance, right? And when you use the definition for capacitance, you divide by the expression for the potential difference. And so the capacitance per unit length, so you divide by length, is something like this. So this is the same answer that you got, right? I hope this explanation is clear to everyone. Okay, I think so. Okay. So now we are moving to a different kind of section that is about multipole expansions. And this is important because we would like to bring the concept of dipoles, okay? And from there, explain about polarization. So that's how we would proceed. We would talk about multipole expansion, and there we would mostly concentrate for now on the electric dipole, and then say that if you have a dipole distribution, and how can that result in net polarization in dielectrics, right? And that's important because we want to finally go to the expression of polarization and use it to see how we can relate the electric displacement with polarization and the total field. So that's how we are trying to proceed. So before that, just because I was talking about capacitance, and as I don't know if the questions in the assignments are same as before, or sorry, or if they are different, but what I mean is, so I saw some of the assignment questions, and there the major questions that they are asking is that if you want to, so they have given the depletion charge density, or they have given the rho in a way, and then they have asked you to find electric field, they have asked you to find potentials, they have asked you to find, I think, then they have said that they are equating the charges, so they want to say what is the charge density and things like that, right, on the capacitor. Something like not capacitor, I think it's a p-n junction question that I was talking about. So the concepts are the same. So there you know the charge density. What you have to do in those kind of questions is you have to use the relation that how electric field is related to charge density. And the answer would be divergence of E equal to rho by epsilon naught, right? And there, so now you know rho, you want to find E, and you know the relation. So you have to integrate over, do an integration, because the relation, obviously rho is related to derivative of electric field, right? So you have to integrate with rho
Kindly,
over.
can you help us in those assignment questions? Like similar questions, kindly, can you please help us? It
So
becomes very difficult for us later.
I know, but I was trying to see some similar questions. I did not find any. So that's why I thought I'll discuss the basic concepts, and then I'll tell you how to relate it to the questions. So basically, see, we did similar questions. We did questions where we had the electric field, we tried to find the potential. I think similar questions are there in your assignments. And then you know the surface charge you want to find, or the volume charge, you want to find the electric field. So the major thing that you have to do is you have to use the correct relations, right? So if rho is given and you want to find the electric field, so what should be the relation that you should use? Right? The relation should be divergence of E equal to rho by epsilon naught. Okay. So there, now you know rho. So rho by epsilon naught is equal to some derivative of electric field. So if you want to find electric field, what do? You integrate over the length, right? So if there is some function of length and there is some charge distribution given, you have to integrate that charge distribution by epsilon naught over the length to find the electric field. And once you find the electric field, obviously you can go to the potential, right? And use all this relation. So whatever, this relation, if you want to then go to the surface charge, maybe, then you can use this relation. So the relations are already there in whatever discussions we did. And then it's just using the same relations, but actually the questions are quite simpler. So you just have to use those identities or those formulas. That's it. Okay. So given rho, if you have to find E, you have to do an integration of rho by epsilon naught over the length. And then from electric field, you can find potentials or whatever physical quantities that you want to derive. Okay. Now, let us come back to what we were discussing. So we were discussing about multipole expansions, and here, so I would not go into line by line derivation, because this you can find in any standard books. But the main concept is that, so when you talk about dipoles, you have equal and opposite plus q minus q charge, okay, separated by some distance d. And basically what it is doing is, first it is taking into account this point charges. So the potential for the plus q should be 1 by 4 pi epsilon 0 q by r plus, where r plus is resistance. And similarly for the minus charge, right? And then what you do is use the laws of cosines from the center. So it's kind of relating the center of the dipole to the, the field point where you want to measure your field. So this is the relation which gives you the value of r, right? And here, as you can see, if you consider that the point is far, so that you can consider the dipole to be, a point dipole. So in that case, you can do this kind of, you can say approximations, okay, binomial expansions. And then this is your expression for potential. So this is important because now, as you can see, for point charge, your potential would go as 1 by r. But here for a dipole, it goes as 1 by r square, right? So this is how, as you can see, for a quadrupole, it goes as 1 by r cube. For octupole, it goes as 1 by r to the power 4, right? So this is how it, and this would come directly from your multipole expansion. So what do you mean by multipole now? So what I mean is that now you think you have some random charge distribution, right? Excuse me. So some random charge distribution, okay? And then which is distributed over this volume. So you take some volume element d tau, where obviously the charge, net charge in this volume element would be rho into d tau, right? Rho is the volume charge density. So then the potential will actually be an integral, right? Over this entire volume, so that you take into consideration all the charges that are there in the volume. And for each of this volume element, you'll have some r, right? So now they have used the similar law of cosines, okay? And it's the same concept that now you consider that epsilon is very small. So you are far, the points are well outside this distribution. So r is quite large. So you can do these approximations. And finally, what you reach to is that you can write r in terms of this polynomials, right? So that gives you a polynomial expansion of potentials, okay? So if you do that expansion, you would get something like this. Now, as you can see, the first term is equivalent to what we were doing till now. It's like 1 by 4 pi epsilon 0 total charge by r, right? And total charge is given as rho d tau. So this is the monopole term, right? Now, what happens for the dipole term? As you can see, you have this r cos theta term that is multiplied. So if you look closely on this term, what you would see is that r cos theta is what? So so cos theta is the angle between theta is the angle between your field point, and the point in your so the position of your charge element, right? So whenever you have cos theta, you obviously actually it's a component, right? So it's like a dot product. So you can write it in this form, okay? And this definition, so whatever you have here is called the dipole moment. So basically, what are you doing? You are multiplying each charge element with its position element, right? So if you have a discrete charge, what will you do? You will multiply each charge with its position coordinate, right? That's what it's being done here. And that is the same integral form is what is being given here. And then if you put that value here, this is the expression for the potential of a dipole, right? And now, if this is your potential for the dipole, and we know how we define dipole moments, like, so this is the dipole moment for discrete system, this is the dipole moment for a continuous system, right? Basically, we are multiplying the charge with its position coordinates. So now, if you are given some charge distribution, what do you think the potential should be? So in order to find the potential, so if you see now in this question, you have said that you want to find the potential. So the first thing that you should do is you should see what is the net charge of this entire distribution. So the net charge is actually 0, right? 4q minus 4q. So that means if you do this term would actually go to 0 because the net charge is 0, right? So what we should then concentrate on is the dipole term, right? And in order to find the dipole term, you have to find the dipole moment. And how do you find the dipole moment? You multiply each charge with its position coordinates, right? And dipole moment is a vector quantity, right? So it will have some direction, some vector form. So given that, what do you think the dipole moment of this distribution should be? Can you try to solve it? Anybody, any idea? So suppose you have this 3q charge, right? And what is the position coordinate? It's given as A into Z cap, right? So the
Ma'am, for the
dipole,
potential, it will be KQ by R, right? So it will be 3 KQ by A.
so that description, that 1 by 4 pi epsilon 0 q by R, so that is the monopole term, right? Then you are considering, okay, so if that is the case, what you do is you do it for each of these charges, right? So 1 by 4 pi epsilon 0 3q by A, 1 by 4 pi epsilon 0 q by A, 1 by 4 pi epsilon 0 minus 2q by A, and 1 by 4 pi epsilon 0 minus 2q by A, something like that, right? That's the
Yes,
monopole
ma'am.
term, right? And so if you add all of them, what would that turn out to be?
That will result to a 0.
Right. And why is it so? Is because the net charge in this entire distribution, so the total charge of this distribution is 0, right? So what you are solving there is you are solving this term, right? This is the definition of potential that we were initially using. That's the monopole term, right? And that turns out to be 0. But we do have other multipole terms. So basically what we are doing is, see, what are you doing? You are considering potentials of individual, this charge, this charge, this charge, and this charge. But there could be, effects of a dipole that might be generated because of these two charges. These two charges are close together, right? So there can be, the field lines would be deformed because of this multiple charges being together. So now if you take these take the four charges in pairs, like first these two charges, then these two charges, then these two charges, then these two charges, then the effect would be, so you would have some extra effects, right? Similarly, you can take four charges together and then you would have some effect. So those effects are being manifested in terms of this different multipole terms. So your monopole term is 0 because the total charge is 0. But now you want to look at the dipole term. And how do you find the dipole term? Is this, right? So what is this? Qi is the individual charges and Ri is the position of that charge in your distribution. That this is for a discrete system. And the same thing goes as this for a continuous distribution. Now you have a discrete system here, right? So here what you have to do is you have to find the dipole moments. Basically now you are taking pairwise effects of charges. And if you do that, you get something like this. Why? Because see, this is the first charge, 3q, and you multiply by the position coordinate that is given as A into Z cap, right? And then you have another charge here, which is q, and it's placed at minus A distance, right? Minus A because in the lower axis. So it's like minus QA Z cap. Similarly, you have minus 2A into A and minus 2A into minus A, right? Along Y cap. So this together gives you a net dipole moment now, right? You have a net dipole moment of your charge distribution. So now if you know P, what you can do is you know that this is the potential for your dipole moment. So you can use that relation, right? So then this is your potential for this distribution at some point, some far point from this charge distribution. So basically R is quite large than A. Okay. And so what you then do is obviously P dot R. What is P dot R? So R is so basically what I mean here is that suppose if you have some, some point here, which is given as P, okay, some point, and that distance, okay, my God, okay, so some point P, and then this distance is given as, R, okay. So what is P dot R? So the direction of your dipole moment is along Z cap, along Z, and this is your position of your field point. So the dot product between them would give you P dot R, right? And if you do that, so if the angle between the two is cos theta, then this is what you get. And if you put that, then this is your expression for the potential of your system. Like, so here you are considering the dipole contribution. You can also consider the multipole, like the quadrupole and the other higher contributions, but their contributions gradually decay down. So the most important contribution would come from the dipole term here. So that's why we are approximating the potential with this formula, right? So now this is important because this tells you how you can define potentials for any given system, okay? And this is the definition. So now if you know the potential, you obviously want to find the field, okay? So there, as you can see here, what is being done is you are finding the negative gradient of V. You know V, and you know that E is related to V as E equal to minus grad V, right? So that means you can find the radial component, the theta and the phi components by doing the gradient of your potential, and that gives you the expression for the electric field. So this is your expression for electric field of a dipole. And this is very, very important for the entire course. It's a very fundamental result, right? Okay. So clear till here, right?
Yes, ma'am.
Okay. So now why did I, for this particular class, why did I stress on dipoles is because now I want to go to polarization. Okay. So what I mean now is that suppose if you have some atom, okay, so you have an atom, so there's a electron cloud, and inside that there's a nucleus, and then you put that in electric field. So what happens is obviously the positively charged nucleus would experience some force because of your applied field, right? The presence of this field would result in some motion, some displacement of your nucleus, okay? And because of that, your atom would actually get polarized. Now, how much would be the polarization would depend on numerous factors. So that, so for a linear term, so basically this polarizability can be a tensor and it can have different values in different directions. But to simplify for now, you can consider that it's a scalar constant, and you can say that that is the proportionality constant between your applied electric field and the resulting dipole, okay? The resulting dipole that originates in this atom because of the presence of this externally applied field, okay? And the expression for alpha, roughly you can calculate by this argument where you say that, okay, so you had this plus Q charge at the center, but then it got displaced because of your electric field by a distance d, okay? And so it got displaced at this distance, and obviously the minus Q electron cloud will be pulling it back. So there would be a balance between the two, which sets it in an equilibrium position, okay? So at equilibrium, the field due to this minus Q charge, which would be pulling it back, and the field, this applied field will be equal, right? So if you do that, you get an expression for the electric field. And you know that your dipole moment is given as Q into D, right? The charge into the position, or so here from the center, like if you can see, if this is your reference, your position is given by this distance D. Okay, so Q into D. So now if you consider P is equal to Q into D, you see that this comes out to be your atomic polarizability. So this in a way tells you that how an atom can get polarized in presence of an applied field or external field, okay? So now think that you have some dielectric where there are multiple atoms, okay? So what will then happen? Obviously, if you have some effective field, some external field, all of these atoms would have some induced dipole moment, right? So there would be a net dipole moment per unit volume element. Okay. So if you can say that your dipole moment, total dipole moment for some, some region, this is a dielectric, suppose. So the total dipole element would be given as polarization P, which is the dipole moment per unit volume into the volume element. And then you are writing the same expression for potential. Okay. And this is some, some mathematical relations which tells us how you can, simplify this. So you can write this expression as by using this identity, you can write it as something like this, and then use the integration by parts formula. So these are just maths, but what's important is that now, so what is this? So you have a dielectric, there would be some induced charges. Basically, that's the take home message. So you have electric field, you have some induced charges that is generated inside the dipole. Okay. And because of this induced charges, there would be some polarization. And because of this polarization, obviously there is some charge distribution. So that would also result in some potential. So one potential comes from the applied external field. One potential comes from the polarization, which is inherent in your system. Okay, so it comes from the induced charges. And that expression is given by this relation here. So now if you use your divergence theorem and the Stokes relations, you would see that you can define this, you can say define this potential in terms of two types of charges. One is an induced surface charge, which is given as P dot n cap, and another is an induced volume charge, which is given as minus divergence of P, where P is the dipole moment per unit volume. That is your polarization. So this is important, how bound charges can result in potentials. Okay. So now, if you want to find the net field in some dielectrics like this, you just can't deal with the field due to your applied charges. You also have to consider the field that comes because of this bound charges. Okay. So this is something that I had discussed in the last class as well, that when we write divergence of E equal to rho by epsilon naught, so there rho is the total charge density. It's not just the charge that is externally provided. It's also the charge that is induced in your system. Okay. So it has this bound charge density and the free charge density. And as you saw that the volume bound charge density, see here, the volume bound charge density is related to the polarization by this relation. So if you put that here, you would get to this expression, right? So this is termed as your electric displacement. So D is given as epsilon naught E plus P. Okay, so this is something we already know. But now this P, okay, so the P, the polarization is related to the applied, the electric field, not only the applied, the total field. The polarization is proportional to the total field for and then if you have a linear system, what happens is you can write it as epsilon naught chi E into E, where chi E is your electric susceptibility of your media. So that comes from the microscopic description. So if you put this in this definition, you get something like this. And this is now important because now you are writing the electric displacement as epsilon into E, where epsilon is actually permittivity of the material. Relative, so epsilon by epsilon naught would be the dielectric constant. So this is the relation I think many of you were telling in the last classes. So this is very important. And so this, along with this, the definition of your polarization would actually tell you that what is the effect of, the free charges, what is the effect of the bound charges, what is the net field, and how is permittivity or relative permittivity rather making a change in your fields or in your potentials or also in your capacitance in all the physical quantities. Okay. So basically now till now we were only dealing with free space. Okay. But now we will consider a dielectric material and we'll see that how this permittivity, this epsilon, the presence of this induced charges, this polarization, how that can make a change, right? So here you have a metal sphere of radius A, which carries some charge capital Q. Okay. And it is surrounded by this shell of linear dielectric material of permittivity epsilon. Okay, so now what would be the potential at the center? So can you tell me how to proceed with this question? So you want to find potential. So what is the first thing that you should now look into? Based on whatever we have discussed so far, if you want to find potential for some, some distribution like that, what's the first thing that you should try to do? I think you guys got tired. Okay, so the first thing that you should do is you should try to find the electric field, right? So if you know the electric field, you can find the potential, right? How? By the relation V is equal to minus integration of E dot dl, right? So now if you want to find the electric field in this region, and you also have to find the electric field in this region between A to B, and the electric field in the central region, right? Obviously, the electric field in the central region would be 0. Why? Because you have a metal sphere, right? And what would be the electric field in this region? Can anybody tell me? Between A to B? Any idea?
It's proportional to the charge of the inner sphere and to the distance between the point A and D.
Okay. And so what is the effect of the permittivity? Where will the effect of permittivity come in?
In the epsilon naught, epsilon r term, we need to change that
By
to the new
epsilon.
permittivity. Yes.
Right. So
That has to be replaced with the new permittivity medium. Instead of the free space, it has to be replaced with
right.
the new
So
permittivity
you
medium.
should get something like this, right? Inside the metal sphere, obviously everything is 0. Outside, like between A to B, you would get something like this, right? And then again, and in the outer sphere, obviously it's again free space. And there you have the same formula, like the similar thing that you get. So now that you know the electric field, you can actually find the potential. And that's straightforward, right? You do the integration and this is what you get, right? So this tells you now that you see your epsilon is actually the ratio of the total permittivity by epsilon naught, that is the free space permittivity, right? So that means it's your potential is actually decreasing by a factor depending because of the presence of your dielectric material, because of the polarization that happens inside the dielectric material. Okay, and that will also affect the kind of capacitance that we get, right? Obviously, if the potential is getting affected, the capacitance will also get affected, right? So this is now a capacitor. Okay, and in the capacitor, now you have filled it with a dielectric. Initially, it was free, suppose, and now you have filled it with a dielectric with dielectric constant of epsilon r. What do you think the effect will be on the capacitance? Will it increase? Will it decrease? What do you think? So what did the potential? Tell me.
If the dielectric medium is very good, then the capacitance will be higher. If it is a weaker
Okay.
dielectric, then logically the capacitance should drop down because I will have a leakage between the two plates. There may be chances of some leakages. If it's a perfect dielectric, or if the dielectric
Okay.
property, the medium epsilon value is getting on increasing, then the ability to store the charges will get increased. So the capacitance will increase.
Right. So, and that is actually because your potential, like you said it exactly correctly. And that can also be explained by the fact that your potential difference is actually reducing by a factor, right? And Q is equal, C is equal to Q by V. So if your potential is actually reducing, your capacitance will actually increase by that factor. So this is a general way of, uh, increasing the capacitance of capacitors by putting some dielectric in between plates. Okay. Now this is another thing, I guess there could be. So this is basically this is what we derived. Okay, we derived it for this concentric shells, right? like two shells and two concentric sphere capacitance. This is something we just derived. But now if you have an isolated sphere capacitor with some charge, that will also have some capacitance. And how do you find that? So there you put A equal to R, A tends to R, and B tends to infinity. Okay, so it's large, the entire space. So if you do that, this is your expression for capacitance that you get. And you can also get it from the potential by using the definition of capacitance. So this is, I tried to put it because this is something which might come in your assignments, and something based on this, spherical capacitors and something like that. So this is the concept that you need to use in those kind of questions. Okay. So now this is a question where you now have a solid sphere of some radius r, okay, and it has a charge density, right? This is some charge density, and you say that the magnitude of electric field at r equal to capital R by 2 is 1.2 times of r equal to capital R. And then you have to find what is the value of A. So this is a very straightforward question, and so I had put it for you to practice so that you get a practice of solving this kind of questions. But I guess you people are getting a bit tired. So I'll try to share the solution. So you have to use the Gauss's law, okay? So your charge distribution is given. You have to find the electric field, right? So what you do is you do E dot dA, right? So you consider some Gaussian surface, right? And the surface area of that surface will obviously be 4 pi r square, okay? And so this is some spherical surface of some radius r, and then we will put the individual r values. So this is for a general surface, and you know the volume charge density. So you can find the total charge that is enclosed in that volume or in that sphere, okay? So this is a general expression that you get as a function of r. And now you use this condition that is given, okay? And with that, you can solve for the value of A. So these are very standard questions which generally comes in, in this kind of topics of electrostatics and things like that. So it's this kind of, so your potential is given, or your surface charge density is given. You want to find potential, you want to find electric field. These are very, very standard questions. Okay. So now this is a very simple and interesting question. So here it says that you have this 4-point charges, right? And this is how the field lines look. So what do you think the electrostatic potential should look like, or how should it be proportional to R? What do you think the answer should be? So it comes, it's a qualitative question which comes from your idea of charge, charge distributions, multiple expansions, and things like that. So what do you think the answer should be? You don't need to solve anything. Just look at the picture and think. Okay, so you can see the charge lines are actually starting from one charge and ending at other, right? There are no arrows, but obviously the linking shows that they are of different polarities, right? Otherwise, it would have diverged. So that means you would have some plus q minus q plus q minus q type of distribution. And as you can see, they are symmetric, right? So this kind of distributions happen for a quadruple kind of distribution. And for quadruple, we know that at large distances, potential goes as 1 by r cube, right? So the answer here would be D. So these are some questions from, JAM and NET and things like that. So this kind of questions do come where these are all qualitative questions based on your normal understanding. Okay. And so this is this part is interesting. So here you have some parallel plate capacitor with some dielectric constant, okay, and it's connected to some potential. The area is given, the separation is given, and you want to find the capacitance and the stored charge. So I won't spend much time here because these are just formulas, right? So you can use the formulas and you can find the capacitance, you can find the total the stored charge, okay, and this also gives the stored energy. That's fine. This part is interesting, okay? So it tells us that now, so these are the values of capacitance and total charge and everything. Now what happens is the capacitor is fully charged. At this point, your battery is disconnected and the dielectric is removed. Okay. So how will your values change? How will your capacitance change? How will your Q change? And how will the stored energy change? Any idea? So you have removed the dielectric. So basically, from our previous understanding, we know that the capacitance should obviously decrease, right? But then what would happen to the other quantities? What would happen to the stored charge and the total charge? Okay. So because the capacitor is fully charged and then the battery is disconnected, that means, okay, after the removal of the dielectric, what would happen is there would be no change in the total charge. There is no way the charge can change, right? So the charge remains fixed, but obviously the potential difference now changes because the dielectric is being removed. So the capacitance do change. The capacitance decreases. And now because your capacitance, gets decreased, so your stored charge and the stored charge remains same. So the total energy, the stored energy will obviously change because while Q is constant, but your C has changed, right? So this tells you, like, this kind of questions are often asked, where whether, in what state your capacitor is, whether you are connecting the, like, when are you connecting the battery, when are you disconnecting it, all these questions would hugely alter the results. Okay, so this is an interesting part, that because the battery is disconnected and it's totally charged, so there could be no change in the total charge, even though the capacitance would decrease. Okay,
I
so
have a question in
basically,
that one.
yeah, yes, right.
Here in
Tell
this
me.
case, I can see the stored energy is increased after removing the dielectric medium. Initially, it was 2.21, and now it is 11.05 after removing the medium.
Right.
So how to understand this one? Like what does it mean? The in- the increased amount of stored energy after removing the dielectric.
So basically, when you are removing the dielectric, it's like there would be some kind of attraction that will be felt between these charges, right? The charges on this two plates, there would be some kind of attraction. So now to keep the charges constant, the charges can't change, right? So so there's no way that it can change, but it would obviously, the interaction between these plates have changed, the potential difference have changed, right? So then you have to do some amount of work in order to put the charges, like keep the charges constant. So that's the physical way of thinking about it. So some extra amount of work has to be done in order to maintain the charges like that, even when you have removed the dielectric. So that extra amount of work comes out in terms of this newly, the that increases the stored energy of your system. What is this energy? It's like how much work has to be done in order to maintain that energy, that charge in the capacitor, right? So
Yes,
that
that is
increases.
what it in an independent case I'm understanding it. If two are separate case, one capacitor I have a dielectric medium filled in it, and then I need to inject an energy of 2.21 microjoules to store that charge. Okay, it's clear. And if it is a medium without dielectric, or my dielectric is removed, then I need to inject a higher amount of energy to store the same amount of charge. That's also clear. But when we are seeing this as a sequence of event, already I stored the energy, already I stored the charges in the plates, and then I'm removing the dielectric. So
Mm.
will this apply there? If it is a two separate events, yeah, it is clear. I need more amount of energy if the capacitance is lesser to store the same amount of charge compared to the first case where the capacitance is higher because of the dielectric. So
Right.
as
So
we are talking about the sequence of event, then that is my question. Why, like what the 11.05 means in that? Because I
yes.
already am
So
storing the charges, right?
see,
The
yes. So see. So basically, you already answered the question. See, you know the individually you can understand, right? So that means, so how do I tell? So this is one condition. This is another condition, right? You have one you have the dielectric, another case you don't have the dielectric, right? But you know that if there is no dielectric, you need to do more amount of work in order to have that same amount of charge there. Otherwise, the charge won't be there. You understand? Like, so
Yeah, I
see,
understood it, but here the condition, as per the question is, the initially dielectric was there. Then the second condition B is it's after it is fully charged, then the battery is disconnected and the dielectric is removed. So after that, whatever the energy stored in step A, 2.21 will remain and it will start to decay in the second half as per condition B. If it is a separate case, I understand. If it is B is a totally
yeah,
a new case, that is different.
but
Here the
see,
battery is also disconnected, then what is the source of the additional energy, or where we are getting that additional energy from the remaining 8 or 9 microjoules of energy?
I guess it's because your potential difference has increased. You know, the potential difference between the plates have increased. So if the potential difference, so you basically have the same charge, right? Same charge on the two plates, but the potential difference between the plates have increased. So that what is potential difference? That is like amount of work that has to be done in order to take the charge from one surface, one plate to another. So if your potential difference has increased, that means the effective energy of your system has actually increased.
It is clear, ma'am. Like what I am trying to tell is
I
the
understood.
first step, we are injecting some energy and storing that amount of charge. Then the source of energy is stopped, which is disconnection of battery. So once it is stopped, then there is no possibility of injecting more energy into the system at all. So if we are considering it's a sequence of event, what I feel is then the
No,
charge
no,
will remain same, and
hmm,
yeah, and it will start to
but
slowly decay or do something will happen in that way. Whereas the energy will also slowly decay from 2.21, it will start to decay. That is what I am
but
thinking.
what I understand is that, so basically this is like some charge distribution, right? After all, it's a charge distribution. So now if your charge distribution had some, so there were some charges at some places and they had some potential difference. Now that potential difference has changed. So basically your charge distribution is now at a effectively higher energy state. It's not that you are providing that energy. The
That's
charges
fine.
have,
If we are discussing in terms of energy, I have given some input energy and I'm getting higher amount of energy when the dielectric is removed. So, like,
no. So you have the dielectric. You have to do some amount of work in order to have some charge at some surfaces. Okay. Now that now that charge distribution has some potential energy,
okay,
some energy of the system. Now you have removed the dielectric. So what you are basically doing is now your system equilibrium is actually changing, right? So
yeah,
your charge distribution, the charges will have like the same amount of charge will be there on the two plates, but the potential difference between the two has changed. So
yeah,
basically the energy of your system would, so it is how the system is actually evolving. You are not putting in
okay,
energy. The system is evolving in such a way that it goes to a higher energy state, and it's somehow related to the tendency of charges to you know uh, decay, or how do I explain? So
okay,
you understand, like the inherent tendency of the charges to actually decay down from that not decay exactly. What is that term I'm forgetting? Like basically
I,
the charges won't be willing, like normally the charges will always be, you know so basically now your system has changed. You are not doing that work. Your system is changing, so the charges are themselves distributing themselves in such a way that they can maintain that potential difference, that higher potential difference between them, even when the magnitude of the charges are the same. You understand? So
okay,
it's like how the system is evolving.
okay,
So I would see, I try to I don't know, I might not be very convincing. I'm trying to think of how to, you know, but I'll maybe again try to see how I can explain it even better. But basically, from my understanding, what I feel is because now your potential difference of your plates have changed, the amount of work that is required for your system to be in that stable state where the same amount of charge remains and but the potential difference is high would be larger. So in order for your uh, so basically I'm just telling the same thing. So so I think
Okay.
that's the explanation, but I would see if I can answer it better. I think you are not very convinced, but yeah,
In
I'll
terms
try
of
to.
potential, I understand because potential is going to change and the capacitance value will change. That is clear because charge is going to remain constant. Up to that,
So
it is clear.
actually, so
But
so that means your
uh,
system. Uh,
according to me, the energy, so where I'm getting the surplus of energy, earlier it was some energy, like we need to give that into the system, right? Without that, how I can get it from the system back? So there is a difference of energy of 8 microjoules. So
yeah,
which means that I'm injecting 2.5 microjoules, I'm getting 11 means then the conservation itself lost here. So what I feel if it's an independent event,
I think the very
I'm
moment you are
uh,
taking the dielectric away, like when you are taking the dielectric away, there would be some kind of, this energy transfer that you're talking about, that like the charge distributions at that instance when you are taking the dielectric, you are removing it carefully. That like that act,
you are
that
trying
that
to tell like impulse energy kind of thing, but here we are totally discussing about the total energy only. So it could be
no
an
no not the
impulsive or it
not
could be
the
non-impulsive, right?
yeah, it can be, but I don't think exactly impulsive. What I mean is this act of removing the dielectric.
Mhm.
So during that action, there will be some redistribution of charges. So this act of removing the dielectric, when you are doing that, there has to be some energy transfer, which would result in the charges to distribute in such a way that they can be there.
Ah,
Okay, like
okay. Now you're saying I got your point. Like now I'm removing the dielectric, which means that I'm letting the free air, or I am replacing with a new thing, or let's consider it as free space. So which means that if I'm replacing with free space means then am I gaining a new amount of
okay,
energy?
I just lost. So I just lost you for the last
Huh.
1 minute.
Yes.
What did you
You're
say?
what you are saying is like if I'm removing the dielectric, like it's charged to 2.21 microjoules. Now I'm removing the
Hmm.
dielectric from it. Let's consider it's again it's filled with a free space medium. Okay. In that
Hmm.
condition, the alter that happened is the dielectric is removed and it is occupied with the free space medium. Does it
Right.
add that adding the dielectric medium, does it add that 8 microjoules, additional 8 microjoules? That's my question. Anyway, I'm little bit not convinced. I also will check the book
I know.
about it. Yeah,
No,
sorry,
I
but
understand.
yes.
No, I understand. Even I'm not able to, convincingly explain what I am feeling. So it's it's basically obviously like that act is actually doing it, but now I don't know how to explain that. It's kind of a so I don't know, like how you are actually changing the entire system conditions. So the moment you are doing this transition, the charges will still have to be there on the surface. So there the work comes in, like you it was in some state, now you are removing the dielectric, but the charges still has to be there on those two surfaces. So that change, like there, this action is coming into picture, so the energy comes in there
Yes.
now.
Yes, I
uh,
got it. Like if it is a separate case, I accept it. If it's a fresh capacitor which does not have a dielectric, then I'm charging it. Then I can understand like I need to inject 11.05 microjoules to store the same amount of charge for the new free space dielectric medium. Yeah, it is clear if it is a separate capacitor. But as a sequence of event, I'm not able
no
to
no
get
even
it.
for the
That's the thing.
sequence of events, yeah, no, I understood. But even for the sequence of events, while you are doing this change, so the act of keeping the charges at the same surfaces, there the work is done, like because you are removing it but the charges are still there, so there's kind of a redistribution that's happening, so that takes it to a new energy state. Now I would look into how I can explain it, in a more convincing way, but like I can feel your question, but like I
Okay.
don't know how to explain it further.
No problem. No problem. Thank you.
Yeah, I'll see if I can, look into it
Mm,
and find some better explanations.
we can see it in next session also. No problem. Thank you.
Yeah, sure. Oh, okay. So now anybody else, any other questions?
And I have one more question, like
Yes,
uh,
yes.
about this capacitors. In case of parallel capacitor, in fact, I was reading something. I just had the doubt. In case of parallel capacitor, okay, I do not have, like, I have two, three capacitors in parallel. That is fine. In case of a series capacitor, let's consider two capacitors are in series. Then the net
Mm.
capacitance is 1 by C equivalent is equal to 1 by CA plus 1 by CB. This is the general electrical formula that we used to follow. But how the field distribution happens if there are two capacitors
How
connected
the
is in series? The electric field distribution happens between two capacitors that are connected in series.
Okay, but so you mean whether there is whether this field inside one capacitor affects the other, the
Yes,
field
yes. How
inside
how
the
does
other?
it affect? Yes.
Okay. Mm,
In case of parallel capacitor, it is very clear because I'm having a big plate, so I can break that plate into multiple parts. So I can get the parallel capacitor derivation, which is equal to sum of
mm,
all the capacitance. That is very simple. But in case of a
yeah.
series thing, so how can I derive that equation, or does electromagnetics say anything about it to derive the capacitance if uh,
No,
multiple
obviously the
capacitors are connected in
potentials.
series? Yes.
Yeah, right. The potentials will obviously have an effect. Otherwise, how do you explain? Like the derivations would be, so here basically now the what would happen is your charges would actually get distributed on this two things, right? If it is in series. So
Yes. Like two capacitor means, let's assume that one plate is for capacitor of one plate is bigger than the other capacitor. So what happens is, in the in between medium, like I have two
mm,
capacitors, so the bottom plate of capacitor A and the top plate of capacitor B, these two
mm.
are of different plate sizes now. So these two are connecting. So how
Oh,
the field
okay.
is set up, so what happens in
Okay.
that
So
zone, this
but
kind of
there's no
thing I want to
there's
know.
no dielectric between those two, right?
Let's imagine all the dielectrics are capacitor 1, capacitor 2, everything. For simplicity, let's assume
No,
both the
no. Yes, yes. So
capacitors
I
are
mean,
having dielectric,
I
same dielectric. Only the capacitors, two capacitors are different because the length of the dimension of the plate is different. The distance is also
okay, okay.
same. Let's consider it's having equal distance, d for capacitance 1 and d for capacitance 2. But only the area of the plate of
Area,
capacitance A,
area.
yes,
Yes. So the
is
charge,
different.
that would be flowing through it, that would get distributed differently on the two capacitors, right?
Yes, for upper plate, the capacitor one, which is near to positive source, that is fine. And the bottom plate, that is also fine. But what happens between the junction, because the two plates are connecting there, uh, capacitor A
Hmm.
plate and capacitor B plate, which are different sizes, are connecting there. So what kind of thing is happening there, or how we are able to arrive at the equation for series
Right.
capacitors, like 1 by C equivalent equal to 1 by CA plus 1 by CB, that we
No,
are
no.
arriving, right?
Yeah, that
So how
that
we are able to reach?
yeah. Yes, I think that is actually there. So I can try to share the derivation because I've done it somewhere. So it's like it's based on that only. Like like mathematically it's possible to explain. It's not that it's just qualitative thing. Just like parallel case, you are doing it like it's mathematically clear. Even here it's clear. So I don't know. I don't remember the exact way of, like I
Mhm.
can't think of at this current moment, but I'll see. I'll share the derivation. But so it depends on. So whenever there would be this, two different areas, the smaller area would the common region that would have some effect. And so depending on that, the charges would get distributed. So I would look into it and I'll tell you. But it's there. Like it's actually possible to mathematically uh, get into that 1 by C equal to 1 by C1 plus 1 by C2 thing. It's actually possible.
Oh, okay,
Even
ma'am.
from the energy point of view is also, I guess it's there. Like the stored energy idea will also lead to the same thing. Like I've done it before, but at this very moment, I am not able to tell you the steps
No problem, no problem. Please
properly.
take your time, no
Yeah.
problem. Let's.
Yeah,
Okay.
I'll see and I'll tell you, but it's there. So it is possible to explain.
Yeah, we can see in
Okay.
the next session. Thank you, ma'am. Thanks for
Yeah.
support. Thank you.
Yeah. Thank you. Anybody else? Any doubt? Okay. So if gonna, so if not, then let's call it a day. Okay. So meet you next day. Okay. So bye. Bye, guys. And happy Independence Day once again. Bye bye.